Hello everybody, this is Doug Young, and in this video we're going to talk about carbon-13 NMR, right? So previous videos we talked about proton NMR. If you haven't watched those yet, you're not quite ready for the carbon NMR stuff yet. But carbon-13 NMR is a lot more simple than proton NMR. There's not as much information in your typical carbon-13 NMR spectroscopy, but there is still valuable information, and it can help us build molecules that we're unsure of. So what is carbon-13 NMR? Much like how proton NMR looked at the protons, carbon-13 NMR looks at the carbon-13 nuclei. So we're talking about carbon-13, not carbon-12, not carbon-14, carbon-13 specifically. That's the nuclei that we can see in the NMR spectroscopy. It has the right spin state. If you look at the natural abundance, though, of carbon-13, it's only like 1.1%, right? Which means there's very little C13 in a given sample, right? So if you make something and you're going to take an NMR of it, the idea is that only 1.1% of the carbons in your sample are actually carbon-13. Most of them, right, are carbon-12. Probably you have almost no carbon-14, very, very little carbon-14. What's the consequence of this? Well, the consequence of this is that in order to detect the carbon-13, since there's so little of it, we tend to do lots and lots of scans. So while a sample may take just a few minutes for a proton NMR, it may take hours and hours, and you might let it go overnight for a carbon-13, like because you want to get that good signal-to-noise ratio. So you can either do lots of scans, or what you do is you'll concentrate, or you'll do both, concentrate your sample, right? So you have a higher concentration of the sample that you put into your NMR. Again, that's just to increase the number of carbon-13 nuclei that you're putting into the instrument so that you can detect them. The NMR still stands for nuclear magnetic resonance. The theory behind it's the same. It's just that now you're trying to look at carbon-13 instead of protons. So you're looking at slightly different magnetic environment. And much like proton NMR, carbon-13 NMR is used to help determine the structure of a compound. Now we're going to talk more about this in a second, but here's an example of a carbon-13 NMR, and you may notice some big differences. One, the chemical shifts go into the 200s, and it's not like just 1 through 12. And I don't have any splittings because most carbon-13 NMR experiments do not have any sort of splitting whatsoever. And so you're not able to fully elucidate a structure, fully figure out a structure of a compound given a carbon-13 NMR spectrum. But it will help you by providing additional information. So let's look at that. If I'm comparing carbon-13 versus proton NMR, right, remember that with proton NMR, you had this idea, right, that the number of signals equals the number of environments, of hydrogen environments. That exact same thing is also true of carbon, right? So now instead of hydrogen environments, we're talking about carbon environments. How many carbon environments do we have? We'll take a look at that in just a sec. If you take a look at the integrations, right, remember that for proton NMR, you had integrations where the integrations were the ratio of hydrogens in each environment. For carbon-13, no integrations. We're not going to use integrations for carbon-13, and that's because they relax at a different rate. And so not all of them fully relax, so the size of the height of your peaks and the area underneath them don't necessarily correlate to how many carbons are in that environment. They correlate more to how quickly are those nuclei relaxing, and that's not always reliable. So we usually don't look at the integrations, again, of your typical NMR experiment. So we don't have to worry about integrations. It's a little simpler. For the proton NMR, right, we had the splitting, this n+1 rule. So I'd get triplets, quartets, doublets, septets, etc. Carbon-13, no splitting. Again, your typical carbon-13 experiment has no splittings. Now, and that's because they're decoupled from the proton signal. Now, you can run experiments where they are coupled together and you can get splitting in your carbon-13 NMR, but that's a very special case. And right now we're talking at sort of a organic chemistry level, like a second-year organic chemistry level. We're not going to talk about those yet. It's more advanced. And then lastly, for proton NMR, right, remember that we talked about the chemical shifts going from about 0 to 12 ppm, and they told us about the environment around those hydrogens. We do see chemical shifts. It's just now that they range from 0 to like 200, 220 or so for carbon-13 NMR. And they do also tell us about the general environment around the carbons that we're taking a look at. And so we'll take a closer look at that in the next video. So overall, carbon-13 is simpler to interpret, right? We don't have integrations to worry about, and we don't have splitting patterns to look at. So we just want to look at how many different types of carbons do we have, how many signals are there, right? So if I take a look at this, right, remember, so number of signals the number of signals is going to equal the number of carbon environments. So in this case, I'd have 1, 2, 3, 4, 5, 6. That's where this thing right here, you can kind of see that it says the deuterated chloroform right there. That's just the solvent. That's not really a peak. That's just my chloroform showing up. So in this case, it looks like I have 8 signals, right? So if I have 8 signals, again, that means I have 8 carbon environments. Or in other words, 8 different types of carbons, right? And I can use that just like I did with hydrogen. I can use that to start to think about what may or may not be my structure. So if I take a look at these, right, number of signals equaling the number of carbon environments, I have some of these molecules written up here twice because I really want to emphasize the difference between a proton environment, right, so number of proton environments, versus the number of carbon environments. And because they're not always the same, right? So if I take a look at this molecule here, this ethyl methyl ketone or this 2-butanone, we'd say that this has 1, 2, 3, right? This has 3 hydrogen environments. I have the methyl out here, the CH2 here, and the methyl there. They're all different and unique from one another. If I'm taking a look at the carbon environments, though, this carbon is different than this carbon, which is different than that carbon, but I also have this carbon right there. I have 4 carbons, 4 different types of carbons here, right? All of those carbons are unique. One methyl's not like the other, and then I have one attached to an O and one CH2. Those are all different things. And note, right, that the number of environments here is different. So in a proton NMR, right, if I did spectroscopy, proton spectroscopy, I'd see 3 signals. But if I did a carbon-13 NMR, right, then I'd see 4 signals. And that's just because this carbonyl carbon right here, right, doesn't have any H's, but it does have a carbon. And so you're going to see a different number of environments for that reason. If I did the same thing for this one on the right, I see a hydrogen. I see a hydrogen on a carbon here. This carbon right here is the same as the one on the other side. Let me fix that. Right, those are the same. And lastly, those are the same. So I'd see 1, 2, 3, 4 environments. If I was looking at, again, proton environments. If I'm looking at C13 environments, I'm going to see, right, these are the same, these are the same, and that's the same. And then I'm out of carbons, right? So here's an example where I have fewer carbon environments than I do hydrogen environments. So this is all just to say, just to emphasize that pay attention to if you're looking at carbons versus hydrogens, they may have different numbers of signals because you're looking at carbons versus hydrogens. Now, in some of them, they will be the same, right? So let's take a look at this one. Right, those are hydrogens, 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 hydrogens. So I have 1, 2, 3, 4, 5 in this case, if you're looking at proton NMR. And if I go to carbon NMR, it's the same story, 1, 2, 3, 4, 5. Right, so carbon-13 would give me the same number of signals. Right, they're not always different, they could be the same. So just pay attention to what the question's asking you, pay attention to what type of spectroscopy you're doing. And then if I look over at this example, right, in this case, I would see 1 type of carbon. That carbon's unique, as are all of these. So I'd get 1, 2, 3, 4, I'd get 7 different types of carbons in this molecule. Now, a lot of them are going to stack on top of each other and be in the same area, but still, I'd expect to see 7 signals. So keep that in mind when you're figuring out the number of signals. Let's take a look at this example. So kind of like I did for the proton NMR, we want to take a look at, well, here's a sample spectrum, right? This is a carbon-13 spectrum. I can tell right off the bat because I don't see any splitting and because the parts per million go up into the 200s. And then I put down 4 molecules that this might be. All right, so this is a spectrum of one of these 4 molecules. First thing I can do right off the bat is simply count my number of signals. I see 1, 2, 3, 4, 5, 6, 7. So that means I just need to go down and look at these and say, okay, well, how many signals do I see in any of these things? Which one of these 4 could it be? So if I look down at my first one, let's see, we've got 1, 2, 3, 4, 5, 6. I only see 6 here. That means that this molecule is not related to this spectrum. This spectrum is not for that molecule. Wrong number of environments. If we take a look at the next one over, I see 1, 2, 3, 4, 5, 6, 7. That could be it. That could be it. That's got 7 different carbon environments, so could belong to that spectrum. I'll leave that. That's an option. If we look at the next one over, I see 1, 2, 3, 4, 5, 6, 7. It could be this one also. That also has 7 carbon environments. And then lastly, this one here appears to have 1, 2, 3, 4, 5. This one only has 5, way off. I need to have 7. So as far as this NMR is concerned, with its 7 signals, it could be either one of these. It could be either one of these. And in fact, it is one of these. So what we want to do now is we want to ask ourselves, okay, well, if I want to know which one it is, I need to know why I have something around 200 and these things around 130-ish and this thing around 30 and this around 10. Like, what's up? What's going on with the chemical shifts? So that's going to be the next video we talk about. So stay tuned, practice this, watch the next video. Good luck.